Welcome back to Calculus 2. We're starting on a new set of topics now that is very different from what we've been looking at before. This is about sequences and series, and we're going to start by discussing sequences. So a sequence is a list of numbers in a given order. For example, the sequence of natural numbers, 1, 2, 3, 4, 5. Anything that actually follows that order is called a sequence. So, it doesn't have to be that. It could be like 2, 7, 12, 17, etc. That one's just adding 5 with each one. It doesn't have to be infinite in length, too. You could have just 2, 8, 14, a sequence of 3 numbers. But certainly it's a list of numbers in a given order, usually denoted this way, where the subscript gives the position. The first one is A1, the second one is A2, etc. In essence, though, a sequence is just a function whose domain is the natural numbers. Because if you input 1, you get this term. If you input 2, you get this term, and so on. For example, this sequence, 1 over 2, 1 over 3, 1 over 4, nth term is just 1 over n, has these terms. And you could find them basically just by doing this function. If I just said a of x, that would indicate it's a function of all real numbers. Since I did n, it indicates it's a sequence. That's the convention, and that you're just plugging in natural numbers. Just some notation notes here. We often use this notation to denote an entire sequence. We'll use b of n to denote a specific term, but the sum, the set of all b sub n's is the whole sequence. And this notation you probably recognize even from back in college algebra. We use these curly braces to denote the set of all something. So now it's the set of all sequence terms, so the entire sequence. And sometimes instead of just writing that, we'll actually just write the formula for the sequence. That's just another thing you might do. You might also write a sequence just by writing out all the terms. If you can write it out either every term listed or write it out with an ellipsis indicating how the sequence proceeds, you can do that. And I know this theory is front-loaded. I think we've only got another slide or two. It's just we're introducing a lot of new stuff, so we need to stop and talk about the notation for a bit. So a sequence can be finite or infinite. We already looked at that. An infinite sequence may converge in value to a limit or diverge. So for example, 1/2, 1/3, 1/4, 1n is a convergent sequence. If you take n to infinity, then it'll approach 0, because this will get tinier and tinier. Whereas this sequence, -1, 1, -1, 1, -1 to the n, it's divergent because it never converges to a number. It never approaches a number. And instead of giving you the formal definition of convergence, I'm going to save that for the next video. In this one, I'm going to give you one more definition. The last thing I'm going to talk about before we get into some exercises is a recursively defined sequence. And this is a sequence in which the previous term is used to calculate the current term. So for example, here we have a sub n plus 1 equals 3 times a sub n. You might ask then, how do we start it? Well, there's usually also a given first term. And I guess I will even say could be in terms of multiple terms. So like in this case, all we need is 1. So then the sequence would go 1, 3, 9, 27, etc. But we also could have something like a sub n plus 1 equal, I'll say n plus 2 equals a sub n plus a sub n plus 1. This is a very famous sequence. It's called the Fibonacci sequence. The first two, a sub 0 is 1, a sub 1 is 1. So it's the sum of the two previous. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, so on and so forth. 8 plus 5 is 13. 13 plus 8 is 21. Fibonacci sequence is a very interesting sequence, especially in these seemingly random places it seems to show up in nature. There's been lots of interesting videos done on YouTube and different places about that, so it might be worth doing, but certainly it's a recursively defined sequence based on the previous terms. So let's look at some exercises. Let's start off by doing problem 4 from section 10.1. It's on page 581. This is our actual textbook. Find the first 4 terms of the sequence. Well, here we have the nth term is 2 plus negative 1 to the n. So, if we find the first term, a sub 1, that would be 2 plus negative 1 to the 1. So that would just be 1. 2 plus negative 1 to the 2. Negative 1 to the 2 is 1, so 2 plus 1 is 3. Then we're back here, because on the odd powers this will be negative, on the even powers it'll be positive. So when we plug in 3, it'll be negative 1 again. 2 minus 1 again will be 1. 1, 3, 1, 3, 1, 3. I only needed the first 4, but there we go. Down here, the first 10 terms are the recursively defined sequence. We have the first term is 2, but every other term is n times a sub n over n plus 1. A sub 2 equals 2 times 2 over 2 plus 1 equal 4/3. Then we have a sub 3 equal 3 times 4/3 over 3 plus 1. So that's going to be 4 over 4 equals 1. Then a sub 4 will be 4 times 1 over 4 plus 1. Is that it? Yep. So that's 4/5. Then a sub 5 is 5 times 4/5 over 5 plus 1. So that is 4/6 or 2/3. A sub 6, 6 times 2/3. Probably could have just left it as 4/6, but oh well. Over 6 plus 1. So that's 4 over 7. I'm beginning to see a pattern here. 4/6, maybe not. That's 4/6, 4/4, 4/5, 4/6, 4/7. Yeah, honestly, and this is 4 over 2. So we have 4 over 2, 4 over 3, 4 over 4, 4 over 5, 4 over 6, and 4 over 7. So yeah, this is going to be 4 over 8, 4 over 9, 4 over 10. And we can do a couple more. I mean, a sub 7. 4 over 11, I think, would be the 10th one. A sub 7 would be 7 times 4/7, yeah, over 7 plus 1. So yeah, that would be 4/8 or 1/2. And so on. If you do notice a pattern, you can sometimes make these things go a little bit quicker by doing that. So yeah, that's our first 2 examples. Let's continue on. So you can find terms. Can you find the formula for the terms? Well, let's see. Formula for the nth term of the sequence. We have 1/4, 1/9, 1/16. I think the giveaway really is on the bottom here, because that's 2 squared, that's 3 squared, that's 4 squared, that's 5 squared. Got to deal with the signs as well, but I think 1 over n squared will deal with the number. Then, as far as the sign goes, that's really easy. If you want to alternate in sign, that's what that's called. You have a -1, and then to the end, we'll make it negative on the odd terms. I think we actually have it on the even terms is when it's negative, though. So I got to offset it. So you can either do +1 or -1. I'll just do +1. And there you go. Always, let's see, it'll be on the first one, it would be squared, which would make it positive. Second one would be cubed, make it negative. Third one, fourth, make it positive, etc. So yeah, this would be our formula. A sub n equal -1 to the n plus 1 times 1 over n squared. And this one, well, we have 2. And you can see, let's see, 2, 6, 10, 14. It's adding 4. So 2 plus 4, n. That'll give me 6 for the first term, so I need to offset this by 1, like so. Then I think it'll work. On the first term, it would be 1 minus 1 would be 0, be 2. Yeah. You can actually simplify it, though. 4n minus 4, 2. So, be 4n minus 2 would give us the formula. On the first one, we would get 2. Second one, we'd get 6, etc., etc., etc. And for our last one for this video, let's try this one. You can pause and try it yourself for a bit. But the top, I can see, are even numbers. So I think we can get away with that with just 2n. Bottom are odd numbers. That's actually, if you know how to do even numbers, it's not hard to do odd numbers, because odd numbers are all the even numbers plus or minus 1. So we just do 2n plus 1. I'll call this C sub n instead of A sub n. I've been using A too much. And there we go. That'll be it for this video. Next time, we'll look at more sequences. We'll look at more theory. Have to prove some theorems. Talk about some different properties of sequences. I think we'll probably be here for at least another 2 videos. We'll see if it takes more than that. Have a great day. Talk to you later.